Hi, it is section 5.5, indefinite integrals and the substitution method. This section will begin with a summary for integrals. The fundamental theorem of calculus says that a definite integral can be computed directly if we can find an antiderivative of the integrand. That is the second part of the theorem. We defined earlier the indefinite integral as the collection of all antiderivatives of f and symbolized by the integral sign. Any two antiderivatives of f differ by only constant, so we can write in this way. The indefinite integral of f is antiderivative, any antiderivative plus arbitrary constant. The connection between antiderivatives and the definite integral now explains the use of notation. Here we have second part of the fundamental theorem of calculus. Integral from a to b f of x dx is same as now the difference of the antiderivative evaluated at b and a. It can be written in this way. So with any arbitrary constant, these are the same. So in practice, when we try to evaluate the definite integral by using antiderivative, we ignore this portion, the constant. It's okay, we can ignore that one. Okay, now here, let's try to solve this problem. Now for this one, for the integrand, we have to find the antiderivative, and we evaluate here from a to b. Here a is 1, b is pi. Okay, so let's try to find the antiderivative. 3x squared, its antiderivative is x cubed plus c. Now we'll ignore the constant. Okay, and here for cosine x, its antiderivative is sine x. Right, quite simply. And for 1 over x, the antiderivative is natural logarithm of absolute value of x. Okay, for this one, we have to evaluate the values 1 and pi. This is a lower bound, there's upper bound. Okay, so that is, now for each term you can do it. So it's a pi cubed minus 1, that is from first term. From second term, now pi, okay, sine pi is 0, and once x is 1, then that is a sine 1. Now from last one, here, once x is pi, then there's a natural logarithm of a pi, and x is 1, then that is 0. If you simplify these terms, then that will be the final answer. Okay? Now we'll go the substitution rule. If u is g of x is a differential function, then now also f is continuous, then the integral of f of gx g prime x dx is same as fu du. That one is corresponding to the chain rule. If you have the composite function f of g, which is same as now f of g, if you put x over there, then it's given in this way. If you try to make a derivative with respect to x, then now d over dx, now f of g of x, then in chain rule, we think this one as a variable, or we consider this one as a block. So that first we try to make a derivative with respect to g of x, which is same as f prime of gx, and now multiply here g prime x. The substitution rule for integral is corresponding to that chain rule. We'll see very soon the detail. Now here we have a remark. As with the differentials, when computing integrals, we have now du is same as du over dx times dx. This is derivative, and these are differentials, so that we can get the substitution method for the integral with here. That is now, if u is g of x, then derivative is g prime x, so dx is same as du. Here, the purpose of this substitution is to replace a complicated integral with a much simpler integral. And here we have the strategy, substitution method to evaluate the integral. Substitute u is g of x, and now and du is same as g prime x dx to obtain this form. Then now you can integrate this one with respect to u, then the result will be a function of u. Now you have to replace u by g of x. So let's see, let's solve this problem, and we'll try to solve this problem using a smart guess, which is the method of undetermined coefficient and the substitution method. Okay, let's start with a smart guess. Okay, the integrand is now 2x plus 1 half power, so that here the given term can be written here now 2x plus 1 and 3 over 2, so that once you are trying to apply differentiation, then the power through the chain rule, you can see that the power will change it to be 1/2 by subtracting 1, and some constant will be multiplied. So that if you put here a coefficient, so that the derivative of the whole thing is the same as that one, then this will be an antiderivative. Okay, so let's begin with this portion. Let's try to make derivative. Then that will be same as 3 over 2 is coming out, and 2x plus 1 here now 1/2 power, and then from chain rule it will become, you have to put here 2. That is same as 3 times of 2x plus 1 now power 1/2. So for this one, if you make a derivative for this term, then now you can get this one, but only the difference from the integrand is now the coefficient 3. It must be eliminated. How? If you are putting here coefficients 1/3 here now, 1/3, then 1/3 will go there, so that along with this 1/3 and 3 will be cancelled out, so that eventually derivative of this whole thing is the same as the integrand, which means that this is an antiderivative. So if you are putting now here c, then this is indefinite integral. Okay. Now, and we'll use a substitution rule, substitution method. Here, for that problem, we start with just define u. So it's called u substitution. So let's start with u equal 2x plus 1. Then from this one, du equals same as, now this is g of x. The derivative will be 2 and dx. Here, du is same as g prime x dx. Right? Okay. Now, and here in integral, you have this portion and that portion. We need the dx. So from this one, again, you can say that dx equal half du divided by 2. So you can write this way. So here the given integral is same as, now 2x plus 1 is u, so that this radical is changed into u half power, and now that dx is changed into half times du. So let's write it again. That is now, okay, and half can be go out, and integral u to the 1/2 du. Now you can find the antiderivative of that one quite easily, right? Okay, so what is it? And here 1/2 is there, and add 1, and it's reciprocal. Add 1 is 3 over 2, and is reciprocal is 2 over 3, and u to the, now here 3 over 2, right? Okay, and now you can put here plus c. We rewrite this one. That is 1/3 of u to the 3 over 2 plus c. But now the last step is replace u by g of x. What is g? This is 2x plus 1. So that that is now 1/3 of 2x plus 1 and 3 over 2 plus c. So we got the same result. For this example, and smart guess is faster. However, for general problems, to compute the integral more accurately, you have to use this substitution method. Okay, and either way you can get the same result. So through this example, you can understand how the substitution method is connected with smart guess, and eventually here relationship between chain rule. Okay. Okay, here we'll evaluate integrals. For this one, apparently here x squared plus 5 can be a block, which means we use u equal x squared plus 5. Then its derivative will be 2x, right? Then you can easily see that du equals same as 2x now and times dx. So this 2x dx will be changed to by du. Okay, so given integral is the same as integral, and x squared plus 5 is now u. So u to the minus 5. Oh no, is 4. So what about that? Is minus 4, and here 2x dx is same as du. Now you can do this one quite easily. Plus 1 is minus 3, so that 1 over minus 3 u to the minus 3, right? And now plus c. Now you are using u here, so that there's a minus 1/3, and u is x squared plus 5 and minus 3 power plus c. That's it. Okay? Quite easily you can do that. Now also for that one, here looks like now 1 minus x cubed is replaced by u, then its derivative is quadratic. So that quite easily we start with u equal 1 minus x cubed. Then du equals same as 3x squared times now dx. Okay, we have here minus, right? That is a minus 3x squared. Okay, but we need here 9 x squared dx. So whole thing is 9x squared dx. So if you multiply minus 3, then it's the same. So that is same as minus 3 times du, right? We multiplied here minus 3 and minus 3, okay? Okay, so here the given integral is the same as now 1 over square root of u, so the u to the 1/2, and now times minus 3 du, okay? So that is the same as, okay, minus 3 is coming out, and integral u to the minus 1/2 du. For that one, you can get it quite easily. You can do it yourself. So I'll stop here. Okay, for that one, also it's quite simple. And 1 over x can be a block, then its derivative will be minus 1 over x squared. Okay, so we have a really good structure, and start with u equal 1 over x, then du equal minus 1 over x squared, that's derivative, and dx. So that this portion is the same as minus du. So here, given integral is changed into now cosine of u times minus du, right? Okay. Okay, so minus cosine u is antiderivative is same as minus sine u, and plus c. Now you are using that 1 over x, and here replace this portion, then that's the solution. Now let's go to the D. Okay. Now for that one, tangent and sec are combined there. Later on in chapter 8, you learn the techniques for solving cosine, sine multiplication with various power, and also tangent and sec, the multiplication. But here we'll see a very simple example. Now, you may consider, for example, the derivatives. What is the derivative of tangent? That is a sec squared. And derivative of sec is sec and times tangent. But anyway, here, derivative of tangent is a sec squared, so that if we are using tangent x as a block g of x, then that is same as a g prime dx, right? So yeah, it's quite simple. Now, u equal tangent x, then du equals same as sec squared of x times dx, right? So this portion is du. So the given integral is the same as now tangent squared, which is u squared, and sec squared x dx must be du. From now on, it's a piece of cake. Okay, so you can finish it yourself. Okay, let's go to another set of problems here. Okay, now for this one, apparently now derivative of sine is cosine, so that if you are choosing u equal sine x, then du will be same as cosine x, its derivative, and dx. So this portion will be changed into du. So the problem becomes very simple. Now, for this one, again, now your arcsine squared and 1 over square root of 1 minus x squared. And so naturally, you may ask yourself, what is the derivative of arcsine? That is 1 over 1 minus square root of 1 minus x squared. So that already this portion is same as the derivative of arcsine. So that you may start with u equal arcsine of x, then du equal same as 1 over square root of its derivative 1 minus x squared and dx. So that the given integral is changed into here now u squared and du, right? Quite simple. Now from here, it's really almost trivial for you. Okay, now it's not really simple for these two examples. Here, if you are choosing u equal 1 plus x squared, this is blah, then its derivative is linear term, first order, but you have here x cubed. So some of you may give up getting the antiderivative, but here usually your eyes make you here lazy. So try to do and try and here by using your hands. So hand will make you a very smart person. Okay, here let's start with u equal 1 plus x squared. Then du is the same as 2x now dx, right? But we have x cubed here. Now du is making 1x, but there are 3 of x, so that you have to express x squared in terms of u. From here, x squared equal u minus 1. So that by using this and this, here x cubed dx, we can express that on in this way. There is x squared times x dx. So what is x squared? That is u minus 1. X dx is the same as now half du, right? So we got everything, and the given integral is the same as, now we use u is 1 plus x squared, so that this portion will be same as u to the half, and x cubed plus x cubed dx is same as half of, okay, let's put here now half, and now there is u minus 1 du. So let's rewrite this one. 1/2 can go out and half power, so that is u to the 3 over 2 and minus now u to the half. Now you can do it quite easily, right? Just by using power rule, you can find the antiderivative for each one. And after getting antiderivative, now u must be replaced by 1 plus x squared. Then you're done, right? You can do it yourself. Okay, for this one, now sometimes for substitution, you have to try more than once. Try one. If it is not working, then try another one and another one, and so on, so that you can get finally good substitution. For this one, now bottom is 2x minus 1 squared. So it is like a second order polynomial. So here now first order. So in the beginning, you may start with u equal 2x minus 1 squared. Start with that. Then here du equal 2 of 2x minus 1 and times 2. So that is same as 4. Now 2x minus 1. Now you have to express here the x dx, especially this x, in the whole thing, in fact, over there, x dx in terms of u and du. But because this constant is not easy, so it is not working right now. So we start with the purposely this substitution. Now then, let's try this one. U equal 2x minus 1. Okay. Then now here du equal same as here now 2 and dx. Okay. Now what is x dx? So probably you can get from this one x, that is x is move 1 the other side, divide by 2, so that u plus 1 now divide by 2. Okay. So here, and so from these two, we can get x dx equals same as x is u plus 1 over 2. Dx is half du, divide by 2. Okay, let's try to write down one more time. Dx equals same as half and du, right? So the dx is now half du. So that is the same as u plus 1 over 4 du, right? So the given integral can be written in this way. Now, here that one over 2x minus 1 squared is the same as, now 2x minus 1 is u, so that is same as 1 over u squared. And x dx is same as now u plus 1 over 4 du. So once 1 over 4 is going out, then that is same as u plus 1 over u squared du. Okay, we can get it now very easily. 1 over 4, and we separate. That is now 1 over u, and plus 1 over u squared du, right? So yeah, 1 4, and then now that is logarithm of u, absolute value. That is minus here 1 over u, right? Okay. Now, if u replace u with 2x minus 1, then that will be answer. Of course, you have to add here c, constant. Okay? You can finish it. I hope you understand the core substitution method. But sometimes, once the integrand involves trigonometric functions, then and you have to also use the trigonometric identities. Here we have very frequently used identities. Sine squared can be changed by 1 minus cosine 2x over 2. Cosine squared is the same as 1 plus cosine 2x over 2. Okay, sine squared, cosine squared is same as here, this term and that term respectively. This is a minus, that is plus. You can easily check that by putting 0 sine squared 0 must be 0. Here, cosine, if x is 0, that is cosine 0, which is 1, so that the term becomes 0. Now, cosine 0 is 1, so its square is 1. So once x is 0, then that's 1, so that 1 plus 1 divided 2 will be 1, so that by putting a point, you can check this one. And its antiderivative can be easily found from here. Now, for tangent squared, it's the same as sec squared minus 1, so that now antiderivative will be tangent x and minus x. So we are using this identity. Now, tangent x, you can write down tangent x here, sine x over cosine x. Now, if you are using cosine x as u, then it can be written in this way. So that now through logarithm, you can find the antiderivative. Now, for this sec x, here we multiply this quantity, that quantity over the same quantity. So this is 1. Then if you multiply here term by term, then top will become sec squared plus sec times tangent. Now, this one, sec squared is derivative of tangent, and sec times tangent is the derivative of sec. So that now it can be integrated by using here logarithm, natural logarithm of absolute value of the bottom. So you can finish the integration. Now, for cotangent x, that is reciprocal of tangent x, so that will be cosine x over sine x. So exactly the same technique can be used to get that one. Now here, for cosec x, we are using this technique. Now we multiply this term over the same term. Then you can see the pattern as in this example, so that you can get now here integration. Okay, so these two are quite special ones, and it's not easy to memorize. However, anyway, if necessary, I'll provide the formula. Okay, it is the end of the section. Okay, thank you.